Welcome back to Codex. Our speaker today is Professor Sinan Gunturk, who is a professor in the math department at the Courant. Professor Gunturk received his PhD from Princeton in 2000 and then spent a year at the Institute for Advanced Study before joining the faculty at NYU. In the time since, he's become a leader in the community. Sinan is known for using tools from sampling theory and harmonic analysis to find digital representations of analog signals. Today, he'll tell us about approximation with polynomials and neural nets. Take it away, Sinan.
Thank you very much, Dustin. Thank you for the kind introduction, and also thank you very much for this invitation. I've said many times that this Codex is one of my favorite seminars, and I cannot make it this semester, unfortunately, due to a teaching conflict, but hopefully next semester things will be different. So, okay, so this talk is approximation with one-bit polynomials and one-bit neural networks, and I'll try to explain what those terms mean. This is joint work with Weylin Lee, who many of you know, a student of John Benedetto's and Courant instructor at NYU. And we have two preprints. They're on archive as of December 2021. And I would like to start with an apology in advance. This subject has a lot of people, well, it builds on the works of a lot of people, directly or indirectly, and almost none of them will be mentioned in this talk because I just cannot do it in a fair way. So please see the preprints for the references. And also, in terms of the math that I will be presenting, I will be stating the results in simplified forms or formulations. So apologies for any of the math being looking sloppy at certain points. At least initially, I hope that won't be the case, but later on it will be a little bit like that. Okay, so first I need to start with a very old theorem. It's approximation by polynomials with integer coefficients. So this is a century-old result. There were two results. I believe they were independent by Pal and Klodowski in the 1914 and 1925 respectively. So consider this the set of all polynomials with integer coefficients. So that's the ring. Typically we denote it by z bracket x, but I will really be thinking of these polynomials as functions on 0, 1, rather than just polynomial objects. So this notation is not necessarily great, but we'll use that anyway. So the theorem of Pal and Klodowski says that if you give me a continuous function on 0, 1, real valued, well, we all know Weierstrass's approximation theorem that we can approximate it by polynomials arbitrarily well in the uniform norm, except we can approximate them arbitrarily well by polynomials with integer coefficients, provided the functions satisfy the obvious necessary condition, which is that the functions take on integer values at the endpoints. The reason these functions need to take on integer values at the endpoints is because all of these polynomials with integer coefficients will also have integer values at the endpoints by the nature of the coefficients and by the nature of the domain. But it turns out to be not only necessary, but also sufficient. So this is kind of surprising, and the proofs that were given by Pal and Klodowski were somewhat not straightforward at all. So the fact that the integer coefficient polynomials are dense, however, there was a proof given by Kantorovich later on in 1931 based on Bernstein polynomials. And it's quite natural, and I will go through the proof of this because the ideas in this proof form the basis of almost everything else that I will talk about. So what do we do? So I am not necessarily going to assume that everybody is familiar with Bernstein polynomials. They are a huge subject. They are a beautiful chapter of analysis and approximation theory. But let's just go through a few basics. So first of all, we are going to fix our domain to be the unit interval 0, 1. Bernstein polynomials generalize to multivariate functions as well. But for now, we're going to start with one variable. So if you give me a function f, how do I compute its Bernstein polynomial of order n, which is a polynomial of degree up to n? It can be less. Basically, we form a linear combination of the basis, Bernstein basis polynomials, which are denoted by p and k. I don't know, can you see the hand, by the way? Okay, so p and k is given by n choose k, x to the k, 1 minus x to the n minus k. We multiply it by the value of the function at the grid point k over n. But this already suggests, even if you haven't thought about this for a while, this suggests that these basis polynomials must be kind of somehow correlated with the location k over n, right? Because we are assigning the value of the function at that point. Now, I'm going to actually tell you a little bit of why this gives us approximations, but let me just mention on the slide that if you form the Bernstein polynomial of order n, then it is fairly classical to show that it approximates f in the uniform norm up to within the modulus of continuity of f evaluated at 1 over root n. So if, let's say, if f is Lipschitz, then this would be approximating at accuracy 1 over root n. Okay, so what are the Bernstein polynomials? The Bernstein polynomials, okay, so these are this is the plot of the Bernstein polynomial basis for n equals, I believe, 25. So you see that they are, well, I mean, it's the kth basis polynomial is concentrated. It's a bump around k over n, but there's a huge amount of overlap. So it's quite different from, let's say, a spline basis, right? A spline basis is by design much more localized. You can readily see that there's a lot of overlap. In fact, it is not difficult to show, although we won't need it here, that the Bernstein basis polynomials overlap over a range of roughly square root of n. I mean, they all have support the entire unit interval, but they can be approximated by a Gaussian function, by the Laplace approximation, and that based on that approximation, one can kind of claim that numerically speaking, they overlap with the kind of neighboring square root n polynomials. So by the way, I'm not tracking any questions. So if there are any questions, I would like, please feel free to interrupt. I mean, I will probably not be able to see them in real time. Okay, so, okay, I went too fast. Now, what I would like to tell you a little bit about is some basic properties of the Bernstein basis, and also why the approximation holds. So far, I have not told you anything about how to compute these polynomials with polynomial approximants with integer coefficients. So far, we're just looking at the Bernstein polynomials. Okay, so we have the expression here. So one thing that you can immediately see, so I should mention at the beginning that one can always interpret Bernstein polynomials in a probabilistic sense using Bernoulli random variables. And I will talk about that a little bit, but you can also approach it entirely based on kind of classical analysis methods. So the first one is that, well, we saw that we have some kind of partition of unity, and it is indeed true, and it follows trivially. If you just expand 1, which is now x plus 1 minus x to the n, in terms of a binomial formula, you're going to see the partition of unity. So this is very important. And the second important result is that if you compute the second central moment of the Bernstein polynomials, you actually find an explicit formula. This is the second box here. So this says something about the localization of the Bernstein basis. The fact that they are localized, but not that localized. So I should make that statement. So one way to see this is if you have n Bernoulli trials, success with probability x, IID, then we can interpret the value of the Bernstein polynomial at x as the number of ways in which the probability of having k successes in n trials. And we can interpret the left-hand side of this equation as the variance of the total number of successes. And we can compute it using probabilistically just by knowing what these random variables are, and we can get that formula straight away. Now, I claim that these two formulas give us immediately the error bound. Again, this is something that you may well have seen in an undergraduate course when you prove the Weierstrass approximation theorem. This is just very elementary, but let's just go through this. So because of the partition of unity, we can express the difference between f and its Bernstein polynomial in the following form here, right? So this immediately suggests using the so I'm assuming f is Lipschitz because it's a little easier to give the argument here. If for general modulus of continuity, it's a little more involved and it's not going to be terribly helpful. So I'm sticking to this. And you see that now we are left with a pointwise bound where the bound depends on the Bernstein polynomials, not the second moment, but the first absolute moment. At that point, we can use Cauchy-Schwarz to pass to the second moment and use the fact that we're both using both of these formulas. At that point, it's just a matter of evaluating these expressions to find that we can approximate up to accuracy 1 over root n. So there's a factor x times 1 over 1 minus x here, which tells us that the approximation actually gets better as we get to the endpoints. But that's, we don't need to, we're not going to be too, it's not going to be very useful for us because when we start rounding it, it's going to start looking the other way around. Okay, so this is so far approximating f by the Bernstein polynomial of f. And now Kantorovich's good idea. How do you round the Bernstein polynomial of f? Okay, so we are going to compute a new polynomial, Bn star, where the expression that you see here, the f of k over n times n choose k, that real number is rounded to the nearest integer. Okay, so now we do get an integer multiplying x to the k times 1 minus x to the n minus k. Well, this polynomial here is already a polynomial with integer coefficients that is immediate. So the combination as a result is an integer, a polynomial of degree at most n with integer coefficients. So you do satisfy the constraint. And now at this point, what is the error bound? Well, the error bound, it just suffices to check the rounding error, the quantization error, because we already know that how well the Bernstein polynomial approximates f. And well, we are making an error of at most 1 per coefficient. So we can easily bound the error by what you see on the screen. The terms corresponding to the endpoints actually drop out if we use the fact that the function at the endpoints has integer values. So there's no rounding error here coming from k equals 0 and k equals n. This is quite important because these functions are bump functions, except at the endpoints they take on integer values. So those disappear, right? When we have that the function has integer values at the endpoint. So now there's a nice kind of neat trick. It's actually this bound. You see, it looks like the Bernstein polynomials without the coefficients n choose k. So they're a lot smaller. In fact, this bound is easily seen to be exponentially small in the middle at 1/2. But its largest value is shown to be 1 over n. So it goes to 0 uniformly as 1 over n. Although if you're far away from the endpoints, it goes to 0 a lot faster. But nevertheless, we have the uniform bound, which is 1 over n. So that's actually the proof of Kantorowicz's theorem. So every function here, we dealt with Lipschitz. Let's say every Lipschitz function can be approximated by a polynomial with integer coefficients up to accuracy 1 over root n, that comes from the Bernstein approximation, plus 1 over n, that comes from the rounding. Okay, so we're going to try to use some of these ideas. Now, I should immediately comment that the constraint that the function has integer values at the endpoints, this can be dropped if we settle with approximation on subintervals, proper subintervals of the open interval 0, 1. So this, again, has to do with the fact that the two terms that dropped, that I said that dropped previously, if you don't drop them because you don't satisfy this integer constraint, then, well, if you stay away from the endpoint, you're only going to suffer from an exponentially small term. Okay, so that's exponentially small. Of course, that c is measured by 1 minus how close you're to the endpoint. So it can be a number that is like 0.99, but it is uniform nevertheless. Okay, so that constraint is there if you want approximation on the full interval, but otherwise it can be dropped. Now there's an interpretation of this result in terms of lattices. So let's define, let's talk about this in terms of a linear algebra point of view. Let's define the kind of the power basis. So x to the k, that's going to be my kth power basis polynomial or basis vector. And I'm looking at polynomials of degree up to n. Okay, so I'm looking at k from 0 to n. Now I can actually have a new basis for polynomials of degree up to n. Here I have p and k. It's like the Bernstein basis, but I have a 0 to denote that I don't have the n choose k in front. So I call this unnormalized, because the moment you have n choose k in front of it, it brings its maximum value to roughly the same value across k. But if you don't have it, then, as I said, they shrink to an exponentially small numbers. Now these two lists are actually equivalent in the sense that they generate the same lattice. Their integer span is the same. So one half of the statement is trivial because every p and k 0 is an integer combination of the power basis by just simply expanding this. But we can also say, we can also do it the other way around. We can write x to the k, again, doing the same trick, writing as x to the k times 1, but written in this form, expanding it out, and then interpreting this as now an integer combination of the p and k zeros. So the two lists of vectors have the same integer span, so they generate the same lattice. So now once we see this in terms of lattices, we can now restate the approximation result by in terms of the kind of density of lattices. So we can say that the lattice generated by polynomials, so here I have the power basis. The lattice generated by the power basis up to degree n, if you compute its distance to any continuous function, that distance goes to 0 as n goes to infinity. Okay, so this is Kantorovic's result. Or at least, I mean, the result by Pal and Klodowski, but the proof that we saw by Kantorovich. So now in this talk, actually, I'm going to be talking about approximation from a much coarser lattice. This is the what I call the Bernstein lattice. So now I will be looking at integer combinations, integer linear combinations of the Bernstein basis p and k. So these have the n choose k in front. So they are scaled by an integer that could be exponentially large in n. So this is, so the resulting lattice, so the lattice generated by b sub n, the Bernstein basis, is a lot coarser as a result. In fact, in each kind of direction k, for each basis polynomial, there are n plus one of them. I am kind of shrinking, or I'm expanding the volume by n choose k, so that overall the volume is expanded by this product of n choose k, which, well, that can be, one can check that it's actually about quadratic exponential in n. So it's a much bigger, much coarser lattice. So we'll see that it is actually possible to approximate from this coarser lattice, meaning that the result that I just stated here holds not just for the lattice of generated by the power basis, but the lattice generated by the Bernstein basis. And then, so here's where the one-bitness comes. We will be restricting the coefficients further to a one-bit alphabet. So going from all integers to two values, here plus and minus one, two odd values, but with the assumption that the function is now bounded. And for compatibility, if you choose the coefficients to be plus and minus one, it is necessary for approximability that the function is bounded by one as well. This again follows from the fact that you have a partition of unity. So any polynomial in the Bernstein basis with coefficients plus and minus one can generate a polynomial which is bounded by one in absolute value. Okay, so now this is the new stuff. So I'm going to first list the result, and then I'm going to talk about why it's true. So this is one of the theorems that we have with weylin. So what does it say? So it states that for any function, for any continuous function on the unit interval, taking values in -1, 1, and for any n integer, there are signs, these are n plus 1 signs, plus or minus 1, such that if you form the polynomial with respect to the Bernstein basis with coefficients, these plus minus ones, then there is a choice that approximates the function up to roughly 1 over square root of n. If you assume, okay, so this has to be stated here. I did not assume it's arbitrary continuous. If it's Lipschitz, then the right-hand side will be of order 1 over root n. If it's has regularity worse than Lipschitz, then of course this is not going to be as good due to the initial term, but I will say more about that later. The important thing is that there are two terms here in the error bound. The first term is the approximation error. It has to do with how well, in this case, Bernstein polynomials themselves can approximate the function. And the second term has to do with how well we can round them by 1-bit coefficients. And now there's one distinction that is visible, is that the quantization error bound, the second term here, only goes to 0 away from the endpoints. If x is 0 or 1, it actually does not go to 0. So this is in the nature of these approximations because, well, it's we don't have any constraint on the value of the function at the endpoints, first of all. So this is what we saw earlier. If we drop that constraint, we didn't necessarily expect to be able to approximate all the way to the endpoints. But also, there's no immediate actually way to, there's no immediate remedy. So meaning that if we were to impose an integer constraint at the endpoint, it's not clear that we can still do this. So I might return to that later on. But at least we have uniform approximation on subintervals of 0, 1. And we also have pointwise approximation everywhere on the open interval 0, 1. So this is actually a special case of a more general result. I mean, I stated it in terms of 1-bit coefficients, but we can also do this with integer coefficients, and we can completely drop the assumption that the function is has the range is bounded by 1. It can be anything. So so this is not something that was available in the original Kantorovich theorem. In the original Kantorovich theorem, there was no way to restrict the range of the rounded coefficients of the polynomial. This is a new aspect of the result. So I might leave this out for now, but I'm just going to talk about the proof, why this works. I know that I will probably not get all the way to the end of this talk. So at least one result has been stated, and I would like to talk about why this result holds. So again, there are two stages of approximation. The first one is approximating f by a suitable polynomial with real valued arbitrary coefficients. And the second stage is taking that polynomial and rounding it. Okay, so the first approximation here is Pn. It has coefficients yk. We're using the Bernstein basis here, by the way. So we're not, it's important that all of these approximations are in the Bernstein basis. And then we're going to take that approximation, and we're going to round these coefficients. The rounding you should not take as simple rounding to the nearest integer. That would not work. It's going to be a more kind of sophisticated rounding in order to make the approximation work. Okay, so one thing also that I should emphasize here is that the initial approximating polynomial, one can take the coefficients to be the function samples, as in the Bernstein polynomial, but one does not need to do that. So that's this is something that also actually is valid for the Kantorovic's argument, original argument. So one can actually change the initial approximating polynomial. This wasn't needed there, but it is needed for us later on when we want to have higher accuracy approximations. So but one thing that does not extend from Kantorovic's proof is that we cannot, as I said, we cannot do simple rounding going from the y case to the q case, because simple rounding requires that we bound the sum of the kind of the Bernstein polynomials, but that's not going to go to 0. They actually give us a partition of unity. In the case of Kantorovich, we were rounding relative to not the Bernstein basis, but the unnormalized one, where which it did not have those n-choose case. So there was a huge reduction. So this is as I said, this is a much coarser lattice. That method is not going to work. So the thing about the Bernstein polynomials is that they are okay. They're a linearly independent list of polynomials. They are a basis for polynomials up to degree n, but they are correlated. You saw the picture that as you go along kind of consecutive values of k, there's a lot of overlap. Okay, they are, as I also said at the time, it can be shown. The details aren't too relevant at this point. Is that there is an overlap of up to square root of n consecutive Bernstein basis polynomials. So this is kind of telling us that, roughly speaking, they're actually working as if they are spanning a subspace of square root of n instead, numerically speaking, and they have a redundancy of square root of n. Now, this is not algebraic redundancy. This is numerical redundancy. Has to do, well, another way to see it is that if you compute the difference of these consecutive Bernstein basis polynomials, well, this is just algebra. One works out the algebra, and one finds that it's actually equal to a linear term here. You can ignore this 1 over x times 1 minus x for now. It doesn't, it's not relevant to the discussion, but there is a linear form that has a 0 at k plus 1 over n plus 1. That's kind of the, that's where the times the Bernstein basis polynomial at degree n plus 1, position k plus 1. So this factor actually peaks exactly at k plus 1 over n plus 1. So where it peaks, this linear form has a 0, so it suppresses the peak. So it's telling us that the consecutive differences of Bernstein polynomials are fairly small relative to their own size. This formula actually can be extended for all values of k, including k bigger than n. This has to do with the fact that n choose k for k bigger than n is 0. So the Bernstein polynomials automatically, if you keep the formula describing them, they automatically disappear for k bigger than n. So this is kind of an algebraic useful feature of them that simplifies calculations. Okay, so how do we use this correlation? We're still kind of discussing why these approximations work and how they work. So these Bernstein basis polynomials vary slowly as we change k. So what we do as a result is we look for a way to map the sequence of coefficients in the approximating polynomial. These are real values, that to map them into a sequence of quantized values such that their difference is high pass, because what they're going to multiply is a slowly changing sequence, right? So as a result, we want that difference, overall quantization error, to be small. Well, that's going to work out if you multiply a high pass sequence with a low pass sequence, right? As a function of k. And this is where this kind of this well-developed toolkit of sigma delta modulation can be invoked. So we're going to see this at the first order first. This is actually it captures almost all the ideas. So this mapping from yk to qk such that their difference is a high pass sequence can be achieved by setting up a difference equation, right? We would like to see it as the first order difference of some uk, except we need to put some condition on the uk for this to be meaningful. And the condition we put is that uk remains bounded independently of k. Okay. Now, there's a way to do it. The easiest one is if the quantized coefficients are integers with no bound. Okay, all the integers are allowed. Then what we do is we recursively solve this equation by setting the value of q sub k to be the rounding of, well, it's a greedy algorithm. You set the value of qk that makes the given uk minus 1 and yk, you set the value of qk that minimizes the size of what uk would be in this equation. Okay, so that's given by this formula, and it follows by noticing that with this choice, uk is simply the rounding error here, and that's, since we're rounding, it's bound by 1/2. So we maintain, if we start from a value that is bounded by 1/2, we maintain that we're bounded by 1/2 forever. Okay, so this can be done. And what does it buy us? Well, we can also do this. Maybe I should have said this. We can also do this with a constraint alphabet, a quantization alphabet of plus minus 1, if the input sequence is bounded by 1. Okay, so the same idea works. The details are exactly the same. So in both cases, what do we achieve? What we achieve is that now we have our overall error, which is now we know it to be a high pass sequence, yk minus qk multiplying the Bernstein basis. We do summation by parts because this is uk minus 1. And then we just kind of stated the formula for the consecutive differences of the Bernstein basis polynomials. And then we're back to an expression which allows us to utilize the boundedness of the uk. And then, sorry about that. And then the rest of it will just simply rely on the same arguments as before, because we can use Cauchy-Schwarz and we can use the partition of unity. So it's the same as here, and we get the error bound, which is of order 1/√n. It is kind of, where did this kind of x and 1 minus x appear in the denominator? Well, it came, going back a few slides, it came from this term in our algebraic identity. Okay, so it's telling us that our bound is not as good if we're close to the endpoint, but otherwise we have, if we stay away from the endpoints, we have a uniform approximation of order 1/√n. Now, this is actually not the only bound we can come up with. We can actually say that the whole thing, because it looks like the error bound may blow up near the endpoint. It doesn't actually. It always stayed bounded by 1, because what multiplies here is bounded by 1, and we have a partition of unity. So the whole thing is bounded by 1 regardless. So that means we can actually take the best of both estimates and, well, simplify it with something like this. It's not, it's an equivalent expression to the minimum of those two expressions. Okay, Now it's I said it before that the approximating polynomial with kind of real coefficients does not have to be the Bernstein polynomial. This is something that I'll get back to, but in the interest of time, let me just try to move faster. So in our preprints, we have a number of stronger results. First of all, we have the results stated for other LP norms. That's the problem with the endpoints actually is handled more kind of nicely with the LP norms. We also work out how to do kind of higher order noise shaping. So that means that we actually look for mappings from YK to QK such that the difference is even more highly oscillating. So one canonical way of doing this is setting up the difference equation to be an nth order difference of a bounded sequence. This actually makes the solution a lot harder. The first order was trivial, starting with second order, and there's an entire kind of huge literature now of how to do this, starting with the works of Dobish and DeVore and myself and others. So this gives us higher accuracy of the quantization error. How much more can we do? Well, at the first order, we achieved 1 over root n. At the rth order, we can achieve n to the minus r over 2, provided the input is actually doesn't go all the way to 1. So it just stays, but it can get arbitrarily close still. So that's not a major concern. Okay, so the higher order accuracy for the quantization error can be achieved. Higher order accuracy for the approximation error. Now, this is where, if you are familiar with Bernstein polynomials, you may know about the saturation problem. If one uses the function values, Bernstein polynomials actually cannot create approximations. It cannot take advantage of smoothness of the function beyond C2. Because what can be shown is that the approximation error saturates at 1 over n. So n times the approximation error of the regular Bernstein polynomial converges to a constant times the second derivative of f at x. So this means this is why one actually wants to use other coefficients, and there are various alternatives to kind of classical Bernstein polynomials, but what we need is a representation again in the Bernstein basis. And thankfully, there was a choice, like there was a result already developed by Micheli and Fehlbecker in the 60s and 70s. So their method actually allows us to compute alternate representations, alternate approximations, I should say, which can take advantage of the smoothness. If f is s times differentiable, it is possible to approximate up to accuracy n to the minus s over 2. Now, you may at this point already wonder, hold it now, if you have s times differentiable, should you not expect accuracy of n to the minus s? Well, it is true. It is actually not, well, there's this whole theory of approximation by positive operators that they all suffer from saturation, but there's also so maybe without going too much into that theory, one should know that the fact that all of these Bernstein polynomials being non-negative, it is crucially important in not being able to achieve higher order accuracy. So one actually needs oscillation of the basis functions to fully take advantage of the smoothness. Okay, so what we are able to do with Micheli and Fehlbecker's result is that, well, they don't actually, one thing that we need is that the alternate kind of approximations, we still need the coefficients to be well controlled. So we show that one can control the size of the coefficients in order to guarantee solutions of the quantization problem that comes after that. So overall, we can combine those two methods to get an overall accuracy of n to the minus s over 2 for s differentiable functions using one-bit quantization. Okay, so that's the approximating with one-bit polynomials. Now, I also advertise one-bit neural networks. So how does that work, right? Okay, so this is now this is not exactly a neural network yet. It's a pseudo network. It's so far in one variable. Okay, so nobody should care about a neural network on R, but let's just do it because everything extends to multivariate. So this takes advantage of what we call the Pascal-Bernstein tree. So the usual Pascal triangle has a kind of a version for the Bernstein polynomials. So what do we do here? We start with 1. Think of it as the function 1 or the constant 1. Each branch here has a coefficient multiplying it. So far, it's a variable multiplier. So here on the left side, we multiply by 1 minus x. On the right side, we multiply by x. So in the second, well, I should say the 0th layer, and then first layer, we have those two forms, 1 minus x and x. Those are actually the two linear Bernstein polynomials of order 1. Like we do this again. But one thing that happens is that in the middle, where two branches come together, we will add them. So the second layer has the Bernstein basis polynomials of order 2. Okay, we go down this tree, and then the third layer has all the Bernstein polynomials of order 3. Okay, so far it's just the mechanics of the Bernstein polynomials. And then what do we do with these Bernstein polynomials? Once you go to the level n or order n, well, we multiply them by coefficients plus minus 1, suitably found, right? And then at the bottom gives us our approximation. So now what we need to do is convert this into a neural network that does nothing but that uses nothing but coefficients plus minus 1. So far, the plus minus 1s are at the bottom layer. That's what we have. But we also have multiplication by x. Now, this if you have actually looked at papers by like Yarotsky or other people who have studied kind of universal approximation by neural networks, you would know that multiplication can be done if you have any kind of nonlinearity, right? So you can do it with ReLU if you want, if ReLU is your choice, but you can actually do it much more efficiently. So the question is there a way to kind of convert all these multiplications by x and 1 minus x and eliminate, only use plus minus 1 as coefficients and only take advantage of the nonlinearity that you have? Well, it turns out that if you choose your nonlinearity carefully, you can do this. So the observation here is this. So we're interested in multiplication by x, let's say, of any number a. We have at any node, we have a number a, and we want to multiply by x. Okay, so this is an algebraic identity. A times x is 1/2 a plus x squared minus 1/2 a squared minus 1/2 x squared. So if we use the nonlinearity, the nonlinear unit, here is sigma, equal to 1/2 u squared, then all we have to do is combine a and x with a plus 1, and then compute their nonlinear functions, and then combine them again with plus minus 1s. They're plus 1 minus 1 minus 1. So that's exactly here, right? So if x is your input, a is the value at any node, then down here we have the sigma of A plus X, and sigma of, sorry, this is sigma of X. There's a typo here, sigma of X. And then we kind of combine them with these plus minus ones. And then down here, we have AX. Okay, so all the coefficients here are plus minus one. The only kind of magic comes from this specific nonlinearity. Now, this shows that any plus minus one combination of the Bernstein polynomials is implementable by a neural network with coefficients plus minus one only if we're using this specific nonlinearity. So now these networks actually have skip connections, meaning that the X that comes as the input variable has to be passed on down. So this is something that we discuss in our paper. There are various ways of formulating this, but if you allow yourself to kind of pass down the kind of the network any value that you have already computed without worrying about the that makes one's life easier. Basically, that's the message. Okay, so that's for one variable, right? How do we do this for multivariable? Now, this is the part that obviously I'm not going to get much into, but the well, I mean, I claimed I was going to, but I realized it was not going to be realistic, but it's all in the paper. So how do you do one-bit neural networks in the multivariate case? Well, the first thing is that one forms tensor products of Bernstein polynomials. So in each variable xi, we compute well, if you have a multi-index k consisting of k1 through kd, you just multiply them by this tensor product. And the multivariate Bernstein basis simply is this new basis. What do we do? I mean, well, okay, the next page maybe just summarizes this. So for each variable x1 through xd, we form their corresponding Bernstein basis polynomials. We know that we can do this with a fixed architecture, and then then we multiply them to form their form this new basis. And then we know that if we can come up with an approximation result using these tensor bases, then this will be implementable as a neural network with coefficients only plus and minus one. Okay, so I will not say more about how we're doing this. The details are in our preprint, but I should say that it is actually a straightforward application of the one-dimensional result. So in that sense, it is not a very satisfactory result for me, at least, but it does give approximability, meaning that any continuous function on the unit cube can be approximated arbitrarily well within the unit cube if you stay away from the boundary. And also we show that if you have extra smoothness, one can utilize it to show improved accuracy. So again, I mean, there are two kind of two results. One is the approximability, and the other is the implementability. Okay, so the implementability is already fairly straightforward due to this kind of nice structure of Bernstein polynomials, provided we have these good approximations. And the approximability is, there's a lot of room for improvement. One thing else that I should say, going back to the one variable case where things are a little bit easier to understand. So the whole upper layer of the network is actually fixed, because everything that that is done here is to compute the Bernstein basis in an efficient way. So in terms of the complexity of the function, all the complexity of the approximation takes place at this lower level where this kind of suitable coefficients are found. So in a sense, the function is, so here it's one variable, but if you have n order n Bernstein polynomials, well, there are n+1 coefficients, there are n+1 bits encoding the function. So this is where the so these networks actually, regardless of their depth, they I mean, everything here, the upper part is an overhead. So if you want to write down the description of these networks, they consist of n+1 bits. In the multivariate case, it's n+1 to the dimension, n+1 to the d. So that's where I will stop. I think we have come to the hour, so I can take on questions. Thank you.
Great. I'm going to smash this reaction icon to tell you thank you, and I encourage other participants to. I'll stop the recording here, and then we'll do questions.